Good morning, class. So I know you are kind of like disappointed with whatever happened. We're trying actually to settle down a couple of things. One is what you want to do with the classes. So I know we're going to put the slides online. That's fine. Lecture, I'm going to record my lectures and also put them maybe on YouTube. I will share the link with you guys. But the major problem we have is the lab and also exams. We don't know really what's the solution when it comes to the exam yet. But when it comes to lab, right now we are thinking about recording the lab by our TA. They will do the experiment and they will share the data with you. Any result that they got, they will share them, and we're going to use exactly same numbers that they are written in the lab manual, and we try to do the experiment, and we share those data with you. And we're going to post some questions, like the pre-lab questions, or say the lab by itself, or the post-labs. We're going to post them on Canvas, and I'm going to assign where and how to do them, so then you can do the online, you can do the pre-lab, post-lab question on Canvas. I'm going to talk about this one, so I'm not going to really right now, I'm not going to go deep and talk about how to fix the lab. When it comes to practice classes, SI classes, I got an email from the Losses Center that they said there will be SI classes, but the practice classes, I'm going to speak with my TA. We're trying to find the best solution to fix it, but again, please give me time. Let me come with the best solution, and I'm going to share that one with you. But for now, I'm going to continue my lecture, and I'm going to focus on the chapter 6, the thermochemistry, and I'm going to continue from the heat capacity. Okay. So the heat capacity, as is written, heat capacity is equal to the amount of heat that you need to apply to increase the amount of heat that you need to apply to increase the temperature by 1 degree. Heat capacity is equal to the amount of heat that we need to apply to increase the temperature by 1 degree. But the problem with the heat capacity does not say anything about the mass. As you see, the formula says heat equal to C delta T. Heat equal to C delta T. Heat capacity is C1 delta T is a temperature. So if I have the C, I will say C multiplied the delta T. It will give me the heat that reaction got, or say maybe by chance loss. Amount of heat that one reaction is gaining or losing under constant pressure, we call it delta H. So again, amount of heat that one reaction is gaining or losing under constant pressure, we call it delta H. If you want to really know what's the meaning of constant pressure, watch it like that if you do one reaction, or if you follow one reaction, and you kept the cap of that container, or say the LMI or beaker, or whatever you were using to do the experiment, you kept it open. So in that case, we say it's exposed to the pressure of the atmosphere, and we assume while we're doing the experiment, the pressure is constant. If the pressure is constant, and in that case, we say heat under constant pressure is going to be equal to delta H. Specific heat capacity. What's the difference between specific heat capacity and heat capacity? Specific heat capacity is the heat that you need to apply to decrease temperature of 1 gram this time. 1 gram by 1 degree. So if I go back here, it says heat capacity is the amount of heat that we need to apply to decrease the temperature of system by 1 degree. But it doesn't say anything about mass of that system. Well, the specific heat capacity, as you see, it says amount of heat that you need to apply to decrease the temperature by the temperature of 1 gram from that system by 1 degree. So we had heat capacity, we had heat equal to C multiplied delta T. C is the heat capacity, and the mass is hidden in it. So you can break this one down to heat under constant pressure equal to mass multiplied specific heat capacity multiplied delta T. And as you see here, heat, when it comes to heat, because it's an energy, you have to write it either in joule or kilojoule. Joule or kilojoule. Then mass, it goes with gram. Heat capacity, I will go through the unit for it, but the heat capacity is joule over gram to degree Celsius. And delta T is subject to the C. If C is CS, it goes with degree Celsius. So then you have to use degree Celsius here. But I need to say this one, honestly, it doesn't matter really what you're using here because you are subtracting two numbers from each other. Whether you're writing in Kelvin or degree Celsius, it's not going to change the story. Okay. I said I'm going to talk about the unit. So we have heat under constant pressure, we call it delta H. So heat under constant pressure, we call it delta H. Okay. Heat is equal to C delta T. So you can say C is going to be equal to QP divided by delta T. Unit, you go with either joule or kilojoule, and this one you can go with degree Celsius or you can go with Kelvin. If you go with degree Celsius, then the unit for C is going to be equal to joule or kilojoule divided by degree Celsius. And this is the heat capacity. Heat under constant pressure, you can rewrite it as mass multiply CS and whole this one multiply delta T. So now rewrite the CS. CS, it will be equal to heat under constant pressure divided by mass multiply delta T. Write the unit for them. For this one, we go with, again, joule or kilojoule. Here we go with gram. And this one, let's say we go with degree Celsius. Then the unit for CS, it will be joule over gram multiply degree Celsius. This is the heat capacity. And compare the heat capacity with, this is the specific heat capacity, and compare it with the heat capacity, and the heat capacity, the unit for it is joule over degree Celsius. There is no place for mass when it comes to heat capacity. Okay. We like to use this one more. Okay. The reason for it, because if I know there is a place for mass, I can go with any container. Let's say you were doing an experiment and by chance, you broke the beaker or Erlenmeyer and you switch to new, container. Even that container is made by, same company, but there is no guarantee that the mass is going to be exactly same as the previous one. Okay. Because the mass is not going to be equal to the previous one, so the heat capacity, it will be a different number, and you need to redo everything from the beginning. But when it comes to the specific heat capacity, I don't care what the mass. Mass, it can be any number. So give me the mass of new beaker or Erlenmeyer, I'm going to put it inside the formula, multiply specific heat capacity, multiply delta T, and that's going to give me the heat. Okay. So now we have a question. It says, tell us how much heat was absorbed when you start with a penny. That the initial temperature for it is -8 degrees Celsius, and you raise the temperature to 37. Okay. So now the new temperature is 37. We started -8, and T2 now is 37. They gave you the mass for it, and also they gave you the specific heat capacity for the penny. I need to say this one. When it comes to specific heat capacity, usually we write the specific heat capacity for pure compound. Okay? Pure compound. And this is here, it says heat capacity of copper. Okay? If I know it's, like it's just a copper, okay, just a copper, I will look to the textbook and I'm going to find the heat capacity of copper. Okay. Let's go through this question. So we have the formula that says heat under constant pressure is equal to delta H. Heat, you can write it as mass multiply specific heat capacity multiply delta T. Okay. They gave you the mass, and the mass is equal to 3.10 grams. And also they gave you the specific heat capacity, and it's equal to 0.385 joule over gram to degree Celsius. Next one, we do have the initial and final temperature. Initial temperature is -8 degrees Celsius, and the final temperature is 37 degrees Celsius. So I'm going to say heat equal to MCS delta T. You go with mass 3.10 gram multiply CS 0.385 joule over gram to degree Celsius. You cross gram by gram. So now I have joule over degree Celsius multiply delta T. Delta T is T2 minus T1. You have the T2 is equal to 37 minus 8. QP will be, I have 3.10 multiplied 0.385. I got this one 1.19. The unit till now is joule over degree Celsius multiply 37 minus 8. It's minus of -8, so it will be plus. And that's going to be 45.0. We have one digit after decimal point, so I'm going to write this one with free sig fig and one digit after decimal point. The unit is degree Celsius. You cross C by C. Now you have the final answer in joule. Multiply 1.19. And I got this one equal to 53.7 joule. Okay. So we're done with this question. So I'm going to switch back to the PowerPoint. Okay. Before spring break, I went through such a formula. I said, energy, the total energy of the universe is a constant number. If it's a constant number, and you want to get first derivative of a constant number, it's going to be 0. So energy of system plus energy of surrounding space is going to be equal to energy of universe. Now, if you are saying energy for the universe is a constant number, first derivative of constant number, it will be 0. So you will get delta E of the system plus delta E of the surrounding area or space is going to be equal to 0. And that one is going to give you this formula. And we know delta E is equal to work plus heat. So I can go with this. I can go with wherever delta I have delta E, I will replace it by work plus heat. I'm going to write this one, and I'm going to say here, if there is no change with volume, if there is no change with volume, in that case, delta V will be 0. Delta B will be 0. If delta B is equal to 0, then work is going to be 0. Work is going to be 0. So I'm going to say delta E is equal to 0 plus Q, which is the heat. So I get delta E equal to Q. Look at this one. Number 1. It says delta E of the system equal to minus delta E of the surrounding area. Instead of delta E, write Q. So it will be Q of the system. And it's going to be equal to minus Q of the surrounding. Delta E, we replace it by Q. It will be Q of the system equal to minus Q of the surrounding. You know the formula for Q? We just did one example, and I'm going to go back here. Q is equal to C delta T, or Q equal to NCS delta T. So it's up to you which one you want to use. It's completely up to you, and also you need to look to the question and see whether you have the heat capacity or a specific heat capacity. So I can replace any Q by NCS delta T or C delta T. Again, it depends to the question. So I got Q of the system equal to minus Q of the surrounding. And I will come with new formula. So I have this one. Delta E equal to Q plus work. And second formula, we said E of system plus E of surrounding is going to be equal to energy of universe. And this is a constant number. If it's a constant, when you get the first derivative of it, it will be delta E of the system equal to plus delta E of surrounding equal to 0. You rearrange this formula, you get delta E of the system equal to minus delta E of surrounding. And the third formula, we said Q is equal to either C delta T or Q equal to MCS delta T. We have work equal to minus P delta V. P delta V. I will go through this formula a couple of slides later. But for now, accept this one from me. If delta B, if delta B is equal to 0, then work is going to be equal to 0. Okay? Work is going to be equal to 0. Look to number 1. Number 1 says delta E Q plus work. If work is equal to 0, then delta E is going to be equal to Q. So I go with delta E equal to Q plus 0. It will give me delta E equal to Q. Okay? Delta E is equal to Q. I'm going to talk about this. We said delta B is equal to 0. How delta B is equal to 0? Volume was constant. So you will say volume constant. you did an experiment, and there was no change with the volume. If there is no change with the volume, then V1 is going to be equal to V2. And delta V is equal to V2 minus V1. That's going to be equal to 0. I got delta E equal to Q. How did I get this one? I got it when the volume was constant. So I'm going to say delta E equal to heat, but this one is going to be equal to heat when the volume is constant. We call this one heat under constant volume. Heat under constant volume. This one is going to be different than delta H equal to heat under constant pressure. Okay. So this is delta E equal to heat under constant volume, delta H equal to heat under constant pressure. Okay. So now I go back to this one, and wherever I have delta E, I will replace it by Q. I have delta E of the system equal to minus delta E of outside. And heat is equal to mCs delta T, or heat equal to C delta T. And I have delta E equal to Q under constant volume. So I get, from this one, I will get Q of the system equal to minus Q of the surrounding space or area. Okay. Q is equal to mCs delta T, or Q is equal to C delta T. So you can go with this. M of the system multiply Cs of the system multiply delta T of the system equal to minus mass of outside multiply Cs of outside multiply delta T of outside. Okay. So I got, we can call it M1 Cs 1 delta T1 is going to be equal to minus M2 Cs 2 delta T2. Assuming 1 is the system and 2 is the surrounding space. Okay. Now practice one question about this one, and the question that you have in your slide. Question says we have a cube of aluminum here I have a beaker, and that beaker, it has water in it. They give you initial temperature for it. They're dropping 1 cube of aluminum in it, and you have also initial temperature of the aluminum. Okay, so we have beaker. Inside this beaker, we have just water. T1 or T1 of H2O is given and is equal to 15.4 degrees Celsius. Mass of H2O is also given and is 105.3 grams. Okay. I'm saying add or drop a cube of aluminum, so and the mass for it is 32.5 grams. So now we have a beaker. Well, we got the grid. Let's say you have the cube or whatever. Has to be actually key square is. Okay, this is the aluminum, and that one is the water. Okay. T1 of aluminum is equal to 45.8 degrees Celsius, and CS for aluminum is equal to, says 0.903 joule over gram to degrees Celsius. CS of water is equal to 4.18 joule over gram to degrees Celsius. They are asking, what's the final temperature? Okay, what's the final temperature? Final temperature, I'm going to say here, T2 of H2O. I'm looking for it. And also, I need to have T2 of aluminum. We need to know this one. That if we drop the aluminum, the hot aluminum inside the beaker of water, and give them enough time, they will reach one equilibrium. When I say equilibrium, I mean at the end, the final temperature, or temperature of water, is going to be equal to temperature of aluminum. So why don't we write this one here? T2 of aluminum equal to T2 of H2. And simply, let's call them just T2. So I'm going to call this 2. I'm going to call them just T2. Wherever I have T2 of aluminum, I will say T2, and same thing for H2O. So I get to here. Q of the system equal to minus Q of outside. Aluminum will be the system, and outside is going to be the one that's bigger, and it will be the H2O. So you go with Q. Q is equal to MCS delta T. You will use this formula. Why? Because I do have the mass and also the specific heat capacity for each. So I go with mass of aluminum multiply specific heat capacity of aluminum multiply delta T of aluminum equal to minus mass of H2O multiply specific heat capacity of H2O multiply delta T of H2. Simply just replace the number, but keep the temperature to that. I'm not gonna work on the temperature for now. I'll try to simplify both sides, and then I will put the temperature. So for now, I have mass of aluminum is equal to 32.5 grams. Multiply specific heat capacity of aluminum is 0.903 joule over gram to degrees Celsius. And multiply delta T. I said, let's get the delta T in, we're going to say delta T of aluminum equal to minus mass of water, 105.3 gram multiply specific heat capacity, 4.18 joule over gram to degrees Celsius, multiply delta T of H2O. Okay, so I will try to get rid of one side, make it easier. So left one, have it equal to 32.5 multiply 0.903. This one is 29.3 or 35. I know I have only 3 sig figs, so we can go with here 3 sig fig. and you cross gram by gram, so you get joule over degree Celsius multiply delta T of aluminum equal to minus 105.3 multiply 4.18. This one is 440.15. Again, here we have, this one says 3 sig fig, we have 4 sig fig, so if we stick with the 3 sig fig here, 3 sig fig, joule over degree Celsius multiply delta T of H2O. Now I can divide both sides by either 29.35 or by this number. I'm going to divide both sides by the smallest number. So next step, let's divide this one by 29.35. And same thing here, we will divide this one by 29.35. So I get delta T of aluminum equal to 29.35. This one is going to be equal to 15.0 delta T of H2. What's happened with the joule over degree Celsius? You can cross this unit, entire unit, by that one. You cross them, so now they are gone. Only thing left is delta T of aluminum. And here I have minus, so I need to put the minus there. It will be minus 15.0 delta T of H2O. Now you have the temperature, and you can put the temperature. T2 of aluminum. I said let's call it just T2 minus T1 of aluminum. I give it name equal to minus 15.0 multiply T2 of H2O, just T2 minus T1 of H2O. T2, we don't have it. T1 of aluminum is 45.8 degrees Celsius equal to minus 15.0 multiply T2, we don't have it, and T1 have it equal to 15.4 degrees Celsius. Multiply the 15 to entire parentheses, and then rearrange the equation to get the final temperature. So I get T2 minus 45.8 degrees Celsius equal to minus 15.0 T2 minus of minus, so it will be minus 15 multiplied minus 15.4. This one will be degrees Celsius. So I have 15 multiplied 15.4. Answer for this part is 231. Okay? And it will be a positive number. So I got T2 minus 45.8 equal to minus 15.0 T2, and this one plus 231. Now I'm going to rearrange this one. Where I will do it, I will add this number to both sides, and also I will add the 15 T2 to both of them. So let's take this part. You go with add 45.8 to both sides. If you add 45.8, it will be T2 equal to minus 15.0 T2 plus 231 plus 45.8. So I get T2 equal to minus 15.0 T2, and this one was 45.8. I get 276.8. So now I will say plus 15.0 T2 to both sides, and I will get 16 T2 equal to 276.8. So T2 will be 276.8 divided by 16. The unit is degree Celsius. This one will be 17.3 degrees Celsius. So we got the temperature, we got the final temperature. Remember, the final temperature for H2O is equal to final temperature of aluminum. And we named them T2. Okay. So now we have the T2 is equal to 17.3 degrees Celsius. So we got the final temperature of, we got the final, sorry about this one. We got the final temperature for both of them. Okay. So now we'll switch back to my PowerPoint. So I went through this question, and next one I'm going to leave it to you guys. Okay. They give you mass of iron, temperature also is given, temperature of iron. This is the initial temperature in Kelvin. The next thing they said that we placed it in a cup that it has 25 milligrams of water. They did not give you the mass, but they give you the volume of water. If you knew density of water, you should be able to calculate mass of water. Density of water is just 1 gram over milliliter. So this volume, 25.0 milliliter, is going to be equal to 25 grams of water. So we do have the mass for water. We have the initial temperature also for water. Initial temperature of water is lower than the iron. So iron is going to lose heat, and water it will get heat. Okay. Next thing, they give you the specific heat capacity for each. Okay. Look to the specific heat capacity. It's given in degree Celsius. So now the question is, do I need to transfer this one to Kelvin? Honestly, no, it doesn't matter. You don't need really to do it, because you're gonna subtract that. When you say delta T, you say delta T is equal to T2 minus T1. Okay. Let's choose two temperatures, for example. So I'm going to show you. Here. So let's choose two temperatures. So we got T2 equal to, say, 100 degrees Celsius. T1 equal to 0 degrees Celsius. Delta T is equal to T2 minus T1. T2 minus T1. So delta T is going to be 100 minus 0. This one still is 100. Mathematically, it did not change the number. How about writing this one in Kelvin? T2, if you transfer it to Kelvin, 100 degrees Celsius of Kelvin, it will be equal to 373.15 Kelvin. And T1, if T1 is in 0 degrees, here, T1 is 0 degrees Celsius, it will be 273.15 unit Kelvin. Subtract these two numbers. If you subtract them and say T2 in Kelvin minus T1 in Kelvin, again, it's going to be 100. So mathematically, it's not really changing the final answer. So, question again, do I need to change it to degree Celsius? No, because you are subtracting them. If you are just subtracting two numbers, it doesn't matter. Okay. So simply, you can cross, the C by K. When I say C by K, I mean this. They give you, here, you go with Q equal to M CS delta T. MCS delta T. Go with this one. Q equal to mass is given in gram. Multiply specific heat capacity given in joule over gram to degree Celsius. When it comes to Kelvin, when it comes to delta T, I'm going to say whatever you give me, T2. If it's in Kelvin, just use it. Minus T1. Use this two number. So this one, I'm going to use it in Kelvin. That one also, I will use it in Kelvin. So I'm supposed to write Kelvin here. Okay. Supposed to write Kelvin and then cross K by C, which is kind of like weird. I told you and I showed you that it doesn't matter really whether you are using degree Celsius or Kelvin. Simply ignore the fact that you are using Kelvin. Just say C. Cross distance. And you will get here in Kelvin by Kelvin, you get the final answer in joule. So again, you didn't need to really transfer the number, from degree Celsius, from Kelvin to degree Celsius. Just simply use any number they give you. Okay. So now I will go and switch to my PowerPoint. And I think we have stuff about work. I need to talk about the work. I mentioned this formula. Work is equal to minus pressure multiplied delta B. Work is one part of the delta E. So delta E is equal to Q plus work. So if work is part of the delta E, and we know delta E is in joule or kilojoule, then work must be either joule or kilojoule. So wherever I have work, I'm going to transfer it to either joule or kilojoule. But I need to think about Q. And I'm going to say, I'm going to mention what I meant by thinking about Q. Okay. So we have this formula that said delta E is equal to Q plus work. Delta E can be either joule or kilojoule. So if you go with joule or kilojoule, then each one of this must be either joule or kilojoule. So if I go with joule for delta E, then heat has to be in joule, and work must be also in joule. But the definition of work is equal to minus P delta V. And remember, from the gas law, pressure, we go with atmosphere. And delta V is just a change with volume. Volume, we go with liter. So when you calculate the work, you go with P multiplying delta B, so it will be atmosphere multiply volume in liter. Your final unit for work will be atmosphere to liter. You cannot add this number, okay, anything that comes with atmosphere to liter, atmosphere multiplied liter, you cannot add this number to heat because they are not coming with the same unit. So we need to fix this one. And conversion is going to be 1 atmosphere to liter equal to 101.3 joule. So wherever you get the work, just use this conversion factor and transfer it to energy, like joule. Example, we have R is equal to 0.8206 unit atmosphere to liter over mole to Kelvin. So now the question is going to be find R in this unit, joule over mole to Kelvin. I go with here R equal to 0.8206 atmosphere to liter over mole to Kelvin. I will say 1 atmosphere to liter is equal to 101.3 joule. If we use exact number for R and also right conversion factor, final answer must be equal to this 8.314. Unit is joule over mole to Kelvin. If you multiply this number by that one, you get 0.08206 multiplied 101.3, it will be 8.312 or 313. Why? Because we're not using exact number of R or the conversion factor. The conversion factor maybe it has some small number there, but if you go with more digit, that's the final answer, and that's the correct answer for it. Okay. So now we have a bunch of questions about work, and one question about the work that we have. It says here, they give you initial volume and final volume, and pressure is equal to 1 atmosphere, and they are asking how much work we did, and find the work in joule. So you go with work is equal to minus P delta B. Delta B is equal to V2 minus V1. Delta B, you go V2 is equal to 1.85 minus 0.10. Unit is liter. So you get 1 point. That one will be 75. And final unit is liter. Now, I need to take this one and multiply it by the pressure. So work is going to be equal to 1 minus 1 atmosphere multiply 1.75 liter is going to be minus 1.75 atmosphere to liter. What we did, we have a balloon. We spend energy. We spend energy to increase the initial volume from 0.1 to 1.85. Remember, we are fighting with outside atmosphere. So we need to spend some energy to increase the volume. Work is a negative number. And we said when work is a negative number, that means we are losing energy. Yes, we are losing energy. Now, I need to transfer this one to Joule. So I go with work is equal to minus 1.75 atmosphere to liter multiply 1 atmosphere to liter equal to 101.3 joule. So you multiply this number and you get 177 joule minus 177 joules. That's the amount of work that we did. Again, it's a negative number, that means we are losing energy. Another question about work. Can I give you some time to think about it? Okay. It says, sorry, this is the wrong, this one is the wrong one. Here. It says, calculate delta E. Okay, calculate delta E when you know the system is giving off 25 kilojoule heat. Okay. So it's giving off 25 kilojoule heat. And we change the volume from 12 liter to 6 liter. Okay. So from 12 liter to 6 liter. And I need to go with this. I need to say delta E equal to Q plus work. We do have the Q. Q is equal to 25.0 kilojoule. Okay. Now, what's the sign for it? Because it says giving off, I will say minus. This is given off. Next thing, initial volume is equal to 12 liter. Final volume is 6 liter. So delta V will be V2 minus V1. You go with 6 liters minus 12. It will be minus 6 liters. So work will be minus P delta V. Pressure, you have it equal to, what is the pressure? 1.5 atmosphere. So we do have the pressure. So we go with minus 1 point. Sorry, minus is from the formula. So it will be minus. Pressure is 1.5 atmosphere multiply minus 6 liter. This one will give you work equal to minus. Minus to minus will be plus. It will be 9 atmosphere to liter. 9 atmosphere to liter. We need to find this one in kilojoule. Why? Because we do have the heat in kilojoule. So if we want to add them to get the delta E, we need to have the work in kilojoule. So I will transfer this one to kilojoule. Remember that 1 atmosphere to liter is equal to 101.3 joule. So I'm going to use this one to transfer it to joule and then kilojoule. I got work equal to 9 atmosphere to liter multiply 1 atmosphere to liter equal to 101.3 joule multiply. Okay. 1 kilojoule is equal to 1,000 joule. So I will use this conversion factor and I will transfer joule to kilo. So I will say 1,000 joule equal to 1 kilo. And work will be equal to 9 multiplied 101.3 divided by 1,000. This one is equal to 0.912 kilojoule. Okay. So we got the work, a positive number equal to 0.912 kilojoule, and we have the heat, a negative number, because the system says giving off heat. So now we should be able to calculate the delta E. Delta E is equal to Q plus work. Q is minus 25 plus heat is work. We got a positive number, so it will be 0.912 in unit for both kilojoule. The final answer, it will be minus 24.09 kilojoule. I think I'm going to stop here for today, and I will post next lecture maybe tomorrow or the day after. Thank you guys again. I need to say this one. Please be patient. We're trying to come with the best, solution when it comes to slide and lecture, and also the labs. So as I told you, for the slides, I will post them. For the lecture, I will try to record them, and I will do my best to get you something useful when it comes to the videos, but I'm not really good, with the editing and other stuff. So please forgive me for the quality. But when it comes to the lab, I told you that we will do the experiments. I will ask my TA to go through the experiments, and they will use exact number that they are written in your lab manual, and then we will share the data that we got. We share them with you, and we will ask you to do the calculation, and based on those numbers that we shared with you, get us the answer for the post lab or for the calculations inside the lab manual. You will see a bunch of quizzes on Canvas that they are related to pre-lab and lab and the post-lab questions. Thank you guys. See you soon.